So I'm just going to jump right into our solution, because I think most of you are familiar with this. So first, in the first phase, we actually just tried to build a simple data set out of Microsoft Academic Graph data. And then we tried a very simple model which was meant to be our baseline that we would use like subsequently in the other phases of the competition. So for the data set, we only used Microsoft Academic Graph data. We didn't use any other external other data sources. Basically, what we did, it was for all the authors of the full research papers between 2011 2015. This was specified as a separate archive on the website. We got all their papers starting with the year 2000. And for all of these papers that we got from all of these authors, we also got related information about them. So the references, the keywords, fields of study, and whatever else was connected to these papers. Then we did a bit of exploring. And one of the first analyses that we carried out was to check for any obvious trends for the accepted papers made by top affiliations in each of the conferences in the competition in the past. So what I mean by top affiliation is we basically consider top affiliations to be affiliations which had a large number of contributions in previous 5 years actually, to these conferences. So we assume that for large conferences at least, the top 20 places will basically belong to more prolific affiliations. Once the affiliations which are prolific across a lot of conferences. So it's very unlikely that affiliations which had just a few sporadic entries in the last 5 years will actually make it in the top 20. That was our assumption anyway. So in the plot we show that the number of full research papers accepted at the KDD conference between 2011 and 2015, you have the affiliations on the x-axis, the number of papers on the y-axis. The length of each line maps the range of the number of accepted papers for each affiliation, and the black dot is actually the mean number of accepted papers. So this plot, once we did this plot for the top 20 affiliations, we kind of figured that the mean number of papers would actually be a very good predictor in how an affiliation will do in the future. So basically in the first phase, we actually computed the probability of a full research papers being published by a given affiliation based on the numbers of all their accepted full research papers in the last 5 years, 2011, 2015. And thus, we ranked the affiliations based on these probabilities, and this was actually the submission to the first phase for SIG-IR. So you can see basically in the table how we did when we computed these probabilities for other years. So basically, for SIG-IR, you can see like an ascending trend when we used, for instance, more years to predict, to compute these probabilities. So when we use data for between 2011 and 2014, we actually got 0.95 in DCG, a 20 score, and this kind of rose as we used more data for more years. And this generally happened for all the conferences, well, except SIGMOD. But usually it was better the more data we used. So this was our baseline, basically, that we wanted to compare against once we developed better models. So in phase 2, our initial models, so our initial model from the phase 1 was actually just using the number of accepted papers. And it was kind of missing out on the fractional contributions of each author in the final affiliation rank. So the relevance score, as it was computed like as the evaluation metric, basically was distributing the paper scores to these authors, and this reflected on the affiliations. So we figured that we might as well just predict the relevance directly, since the evaluation metric was using it anyway. So then we trained our models to do exactly that. Then we did a bit of extra exploration. So we checked if the number of full research papers actually correlates with the total number of papers for each of the conferences in all the 5 years. So because besides the research papers, there are usually, in the Microsoft academic graph, you have other types of papers as well. So you have workshop papers, journal papers, posters, etc. And they are not specifically marked. So we plotted this number of papers on the y-axis basically versus all the years on the x-axis. And you can see that for each of the conferences, these two numbers actually look correlated. So then we're going to use this actually to grow our data set and improve our predictions. We aim to use two types of models, gradient boosted decision trees and mixed models. And the first has a very good predictive power, and the second one is actually, so the mixed models we use to get like better interpretability. So we basically use this correlation that I mentioned before to extend our data set, and we considered all the papers when we trained our models to do the predictions. We basically built our data set as, you can imagine, like as combinations of conferences times affiliations times years, and then coming like all the other features that we built. So you can kind of get a picture of the shape of our data set by now. You can see that once we used all the papers, the number of observations that we could train our models on grew from several hundreds to several thousands. We already know that the mean historical relevance is has a very strong impact on how an affiliation will do in the future. So besides this, we created new features. First, we compute simple statistics of the relevance from past, using past historical relevance. Then we try to capture how the relevance actually, the relevance across windows of last X years. So last year, last 2 years, last 3 years, and so on, going like 4 years back. And then another set of features is actually built using something that we call the author impact factor, or IIF. You can see more details about this in the paper. But basically, so with this, we tried to actually capture an author's trendiness in the past years. So by focusing only on how their performance was in terms of citations in the last years. We also, so the way the IIF is computed is just simply the number of citations that an author receives for work he has published 5 years back. We also did a few features on using like weighted moving averages of previous relevant scores, where we just chose the weights ourselves manually to give more importance to more recent observations. And our final submission, basically, to this second phase was the prediction made by a single gradient boosted decision tree model using all the papers from 2011, 2015, and the features that I mentioned. In phase 3, we wanted to, now because we saw the boosted decision trees model was doing so well, we wanted to give it more data. So we tried to extend our data set even more. So most researchers publish work at various conferences. However, they do specialize in certain fields. So whatever conferences that they send their work to, they're going to be similar in some way or another. So we use the authors and the keywords from the Microsoft academic graph related to each of the papers that we already got in our data set to cluster the similar conferences together. The assumption is that the information from the related conferences will actually enforce the patterns that we already discovered using our models. And also prolific affiliations are usually prolific across also related conferences, not just those conferences in the first place. So we use Jaccard similarity to compute this related conferences, both in terms of common authors and in common keywords. And from this, we can determine, for instance, which conferences are more similar to KDD. And you can see that in the table. Top down, the more similar, the higher up they are. And with this, we try to expand the data set even more. And since then, we saw that the number of full research papers is actually correlated with the total number of papers an affiliation has at a conference. And although this is only marked, we only had access to this data from 2011 to 2015, we assumed, however, that this phenomenon also applies to earlier papers. So we simply used all the papers from year 2000 and onwards. We just thought like it's going to happen for those papers as well. And then you can see that in the final phase, for the conferences in the final phase, once we added up related conferences, for some of them actually we ended up with almost 100,000 samples to train on. In terms of features, in this phase, we basically kept all the features that we had in the second phase because we did so good. We turned up on the third place, but we just wanted to refine them. So basically, we besides the simple statistics that we kept using which are computed across all the years, we introduced new features based on these same statistics, but on windows of up to 4 years back. So you can imagine it, like instead of computing it for the entire 15 years, we just computed it for the always up to 4 years back. So last year, 2 years ago, and so on. Also, besides, you remember we used the weighted, manually chosen weights and weighted trends as features in the first phase, in the second phase. But in this third one, we actually replaced the features based on the weighted trends with a set of more accurate time series based trend measures. So we used the drift trend to kind of capture the increase or decrease of the relevance according to sort of the mean change over time. We also created 5 more features based on simple exponential smoothing, where for 4 of them we fixed the smoothing parameter ourselves to give more or less weights to recent observations. And for one of the features, we just found the best parameter, the smoothing parameter that best fits the data points. So it's an estimated parameter. And the final step in phase 3, which I believe helped us, was to tune the models in terms of which features, configurations, and how many related conferences we used to grow our data set, and for each of the conferences. So we test our models, basically we combine the features all the features that we have in different groups. So we create these feature sets, and then we do all the combinations together with the number of related conferences, from like 5 to 20 related conferences. And the idea is that we wanted our model to test like the gradient boosted decision tree model and the mixed models to outperform the baseline that we knew already worked. So basically, in our final submission was the predictions made with different feature sets and different number of related conferences, such that the boosted decision tree model would beat the baseline across all years. So even if we trained with data from 2000 to 2011 and we predicted 2012, we still wanted it to be better than the baseline. Just like if we trained with 2000 to 2014 and then predicted 2015. So you can see that with the solid line, you can see the results for the gradient boosted decision tree model, and this is the results for the baseline. And this is NDCG 20, and these are the years on the x-axis. We also used the KDD data from 2016 to also just get an extra validation. So the key points, we only used the data from the Microsoft Academic Graph. We didn't crawl or use any other data sources. We started simple. We set up a baseline, and then we started to gradually improve our models phase by phase. We grew our data set once we kind of set on some models. We grew our data set in each phase, and this actually improved our predictability. And finally, we tuned the models so that we could always outperform the baseline. as you guys said, the public leaderboard wasn't useful at all. So we tried to do this process by ourselves. I didn't mention anything about the mixed models. We used it to see how interpretable our results are, and just to get like a validation regarding the feature importances, for instance, that we got from the boosted decision trees, and see whether they are statistically significant in the mixed models as well. But they generally performed worse than our final models. So that's it.